So I just want to finish beams. I think we are taking time on beams. I'm going to finish beams today so that tomorrow we can start with lamina. So today I'm going to be starting with question 5. Someone asked, I think it's on Friday, about the concept of cantilever or a built-in support. So we are going to be looking at that now. Like, how do you? Okay, question 5. To me, I would say that the concept of built-in support or the cantilever, I would say that is much more easier as compared to the one of simply supported beams. If you want to do your calculations, you want to draw your shear force and bending moment diagram, the calculation is less as compared to that of simple support. If you look at this diagram now, you have to draw a shear force and bending moment diagram. Of course, before you can draw a shear force diagram, you all the forces on the beam has to be determined. Everything has to be determined. So there is a force here that we need to determine, which is Ra. Remember, this is a cantilever or a built-in support. So it's been built in here at this point here. So I think the only force that is missing here that I need to calculate is Ra, which is the reaction at A there. That's that force facing up, which is quite easy because I'm just going to use the concept of upward and downward forces. I want you guys to take note that um, there is a force acting here because we have a UDL that is occupying a span of 3 meters. So 15 times 3, this is going to be what? 45 kilonewton. So I'm just going to use this to get the reaction at A. Normally, when you have a built-in support, I think it's because it's according to your level. I think it's when you're doing stress analysis and all those things. Normally, it has two reactions. We call this one Rx, and then we call this one what? Ry. But according to your level, I think when you are doing your degree, that is when we consider those two forces, the vertical and the horizontal. Whenever there is a built-in support somewhere, there is a vertical and horizontal because the beam cannot move um, along this axis, and it also cannot move vertically except if you want to break the beam. So we have a resistance on the x direction and on the y direction. But when you are doing your degree, that is when you will actually consider all those things. But for now, I think they just put that force there of Ry. Okay. So my upward forces is Ra, and my downward forces are the 45 kilonewton there and what? And 20 kilonewton. So the reaction at A there is what? 65 kilonewton. So this is 65. Remember, when you are doing your diagram, your shear force and bending moment diagram, you need to first draw the beam, like I said, and then make sure that you draw the shear force diagram just exactly beneath the beam, and then the bending moment diagram beneath the shear force diagram. Don't separate it the way I normally do mine because of space, so that we can easily see what is going on at that section. With the section B, what is going on at the shear force diagram, and then at the bending moment diagram. So you can easily trace the section down. Okay, so I've gotten my reaction there. So let me calculate my moment. The bending moment at A, let me start from the extreme left there. So we have section A, we have section B here, section C, and section D. If I want to calculate my moment at that section of A, I'm going to be working from the right hand side to the left hand side because there is no force after the reaction of A, because that is exactly where it is supported. So I'm going to be using the sign convention as usual. So I'm going to take my force. I have 20 there because 20 is facing down. So I'm going to write this as minus 20 multiplied by what? The distance from that point here to the support is what? Is 4.5, because the distance between this is 2.5 meters. So that is 3 minus 0.5. So it's going to be 2.5 plus 2. So it's going to be 4.5. Then plus, I have my minus 45 there, multiplied by that will be 3.5. This distance here is 1.5. 1.5 plus 2, that will give me what? 3.5. Can someone give me the value of the moment at A? Then with the moment at B, that is the moment at the section of B. I'm still going to be working from the right to the left. So I'm still going to have my minus 20 multiplied by, this is 4.5 and this is 3.5. It's going to be minus 20 multiplied by what? 2.5. Then plus minus 45 multiplied by what? 1.5. Then the moment at C, is going to be, I have a distance of 0.5 there and 15. So it's going to be 15 multiplied by the distance, cos of the UDL, multiplied by the half of that distance, which is 0.5 over 2. Can someone give me the value of the moment at A? Thank you, Jonathan. Minus 247.5. Don't forget the unit, kilonewton meters. Moment at B. Thank you. Minus 117.5 kilonewtons meters. Moment at C. This is minus here. Don't forget it's minus 15 times. It's going to give you minus something. Thank you. Minus 1.88 kilonewton. So now let's draw our shear force bending moment diagram. So what I'm going to do, I think I need this diagram. I'm just going to crop that. So let's do our shear force diagram here. That's the length of the beam. So I'm just going to put my section there, section A. Hello, how are you? Section B, section C, and section what? And section D. So at A there is 65. So I don't know, maybe you're going to be drawing according to, so you put your 65 there and just write it as 65. Between A and B, there is no force. So that force is going to act until, the force is going to be constant until um, until B, also going to be 65 here. Now between B and C, between B and C, there is a force that is in between B and C there. So between B and C, so that's going to be 15 times 2.5. So that's 2.5 there. So the center force here is going to be what? 15 multiplied by 2.5 meters. 15 times 2.5. 37.5. So I have a force of 37.5 acting between B and C. That's the span there is 2.5. So it's going to be 65. It's going to be 65 minus what? Because it's acting down minus 37.5, which is acting down. It's going to give us what? 27.5. So 27.5 up until this point here. Let me put that up here. This is 27.5. At C there is a force acting down there, which is 20. So it's going to be plus 20. It's going to be minus 20 plus minus 20. That's going to be what? Minus, no, plus 7.5. Just at this point here. This is positive, right? And the force, this force is acting down, which is negative. So it's going to be minus 20 plus 27.5. So it's going to be around here. 7.5 is going to be around here. Still plus 7 point what? 7.5. Now between C and D, there is another force that is going to be acting there because there is a small UDL load there. It's going to be 15 times 0.5 minus 7.5. It's going to give you what? It's going to give you 0. You're going to have that 0 there. So what you are now going to do is to join the point. You have your straight line there. Going to be another straight line there. There is no force acting in that section. I'm going to have this to 27.5. I'm going to have another line coming down plus 27.5 to 7.5. And then because that is a UDL there, it's going to come like a straight line joining them. Okay, so this is my shear force diagram. Let's draw the bending moment diagram. I'm just going to, I need the values here. Okay, bending moment at D is 0. This is D. This is C. We have B here. And then we have A here. With the look of things, everything is going to, this is 0. Bending moment at C is minus, let me label A, B, C, and D. Minus 1.88. Minus 117 minus 2247. Well, that will be down, 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 down there. So with this one, you just draw a straight line. Draw another straight line to join this point and this point. Okay, so the rest is going to be concave up, B and C. I didn't draw this according to scale, so I don't know how. It was actually supposed to be something like this. So we have D here, we have C here. This is going to be D, this is going to be C, and this is going to be what? B. Because I didn't draw according to scale, so that's the reason why it's looking in that way. Supposed to be a curve that is going up to point D. Let me just use tie to draw it like this, so it will look perfect. Okay. Minus 117.5, and then this one is minus 247.5, and this one is 0. Who got it? Everyone. Did you manage to draw it? It was an assignment. Did you guys manage to draw it? No. Okay. What I'm going to do in question 3 is that I'm going to show you how to draw the beam. I'm just going to interpret the question. Then I'll allow you to calculate the reactions and draw the shear force and bending moment diagram. Okay, this question 3 right here. Because if the diagram is wrong, everything is going to be wrong. You can just compare, for those of you that have done it, you can just compare your 10 meters long, supported at A at the left end. Whenever I see a support, I'll just put a reaction there. So this is A. And D, 2 meters from the right end. 2 meters from the, this is the right, there's the left hand side, this is the right hand side. 2 meters from, let's just assume this is 2 meters. So I'm going to name that what? RD. So that's my section D. Beam carries the following load, concentrated load of 30 kilonewton at B, which is 2 meters, 2 meters from A. 30 kilonewtons, 2 meters from A at B. So this is point B. Another load of 15 kilonewton at C, which is 3 meters, 3 meters to the right of what? To the right of B. So from B, you measure 3 meters. You have your 15. You have your 15 kilonewtons there. This is 3 meters. Another load of 40 kilonewton at E at the right end. So it's going to be exactly at the right end here, which is 40 what? 40 kilonewtons. Meters. So this is going to be what? Point E. A UDL 30 between point A and B. This is C right here. So between point A and B, there is a UDL here. 30 kilonewton per meters. Make a neat sketch, which is what we have done. Calculate the reaction. Now I'm going to leave you to calculate the reaction at A and the reaction at D. Oh, UDL 30 kilonewton per meter between A and B and between C and D. Okay, there is another one here as well. UDL. This is 2, 3, 5, 5 plus 2, 7. That distance there is going to be what? 3 meters. 30 kilonewton per meter. So this is the diagram. After getting the reactions, you determine the moment at A, at B, at C, at D, and at E. I'm giving you 10 to 15 minutes. Between 10 to 15 minutes, you'll be done. If you need assistance, let me know. I will explain to you. 7.5, 147.5. Okay, Jonathan. When you are done with the reactions, you can try and determine the moment at each section. That's correct. Can continue with the moment. It seems you guys are getting it now. Just give me the reaction. What I'm going to do, I'm just going to write out the equation for the moment at A, B, C, D, E. And I'll just leave it. There is a force here, which is 90 kilonewtons. For those of you that were unable to get your moment, you can check my calculations there. That is how you will get the moment at each section. So you just have to punch it out in your calculator. So guys, when you are done, I want to use the remaining minutes to complete marking here. So tomorrow we'll be looking at centroid of lamina. Now the next aspect is determination of centroid of lamina and the center of gravity of solids. But questions are normally coming out from the first aspect, which is the centroid of lamina. I don't know why. I think for the past 2 or 3 years now, I've not seen question coming out on center of gravity of solids. But we are going to be looking at that as well. But we are going to be focusing more on the first aspect, the centroid of lamina. How do you determine the centroid of lamina? So it's basically We are going to be doing calculations on how do you determine the x and y coordinate of a lamina, the x bar and the y bar. So we have the rectangle, we have for disc, we have for half cycle and triangles. So we are going to be looking at that tomorrow. Let me see. It's activity 4.3. You can read ahead, you can go through the examples, but I'm going to be analyzing this tomorrow. And then from then, if you have time, we'll look at center of gravity of solids. Then we'll be done with statics. Questions are always coming out on beams. So that one is standard. So for those of you that have not completed question 3, you can continue. This is where we are going to stop today. And we'll continue from here tomorrow. Let me use the remaining minutes to mark.